All right. Hello, everyone. Thank you for tuning in to today's Corundum developer meeting. So let's go ahead and get started here with some status updates. That's the main thing I have planned at this point is just going through these couple of slides here. One thing I did do is clear out a lot of the old carryover stuff from previous weeks. So I'll bring those slides back, if they become relevant again as I'm working on stuff. So let's go ahead and start from the top. We got a couple of the status of mainly the FIFO memory interface or inference bug that we brought up previously. And they got some simulation related stuff, priority flow control, the AXI virtual FIFO, and then finally some discussion on the potential switch version of Corundum. So let's go ahead and get into it. All right, so first up, the FIFO memory inference bug. Talked about this before, so I'm not going to go over too much detail. Do we have any status updates on this, Ulrich? Do we know? Intel is still working on it, or have we heard anything back?
A little bit inconclusive, but they asked us to retest with 22.4, but I'm not sure if actually it has been really fixed or if they just force it into the M20K workaround. We'll see. So we haven't run this yet, but
Okay.
I think I'll kick this off this week and then we'll see.
All right. Well, one of these things, maybe it's fixed in the latest version of the tool. All right. Well, we'll give it a shot, I guess, and see what happens. Good to know. All right. Let's see. So another tool-related thing. For quite some time, Verilator has been broken in terms of how CocoaTV interfaces with it. I think there was like one specific version that was released that worked, and then the version after that, there was a change to the VPI implementation that broke CocoaTV from working properly. So last week they released Verilator 5.006 that included finally a fix for that particular issue, and so now CocoaTV works again with Verilator. Now, if you're not aware, Verilator is a much faster simulator than Icarus Verilog, and that should, if we can use Verilator instead, that should significantly improve the simulation performance. So I'm starting to take a look at running the various simulation models with Verilator, as well as running all the library code, so all of the Ethernet and AXI stream PCIe stuff, just to make sure all that runs correctly, and then adding it to the continuous integration pipelines and whatnot. It looks like there might be a couple other little bugs that need to be sorted out. There's something related to CocoaTV bus that's causing Verilator to get screwed up. Partially a Verilator bug, but seems like something we could probably work around on the CocoaTV end. So I submitted a pull request to fix that. So we'll see what becomes of that. Hopefully we can get that squared away quickly. And then eventually I'm also going to take a look at all of the lint complaints that Verilator is producing and probably make some adjustments to the code. Verilator has a highly pedantic linter, and there's probably some stuff that should be addressed and adjusted accordingly. And then the other thing that I've been working on for far too long over the past couple of weeks is making some adjustments to the simulation models, all of the CocoaTV extensions that are used in Corundum. I don't know if you've ever run into one of these situations, but it's like you're trying to accomplish one task. Partway through that task, you run into a roadblock. So you start working on that, and then you run into another roadblock. So you start working on that, and you run into another roadblock, and eventually you're like 10 levels down going, geez, how do I throw a Stack Overflow exception, and get out of this mess? So yeah, that's what happened when I was trying to make some simple modification. But after digging myself out of that hole, I got the CI working again, and I had also figured out what was the code coverage has been broken for a while. I finally figured out what was going on there and got that fixed. So, and I learned more than I wanted to know about how coverage collection works in Python, but whatever. That's now fixed. And the other thing I did is I discovered some changes that I had lying around for improving the simulation performance of most of these bus functional models. So I went ahead and took a look at applying that, And the gist of it is basically to put the sources and sinks to sleep, if you will, when there's nothing going on. So basically, instead of waiting for the clock edge event always, if there's no data currently being sent, we'll await something being enqueued, or we'll await t-valid going high, something like that. Save a few CPU cycles and make things a little bit more efficient. I think the upshot of this is after I implemented all these changes, one of the main Corundum integration test benches that I was running, it took about 4 minutes and 20 seconds before. After these changes, it took about 4 minutes. So shaved off 20 seconds. That's decent. We'll see how much more we save once switching over to Verilator, but that might be a little while. All right, so that's about it for the simulation updates. Now, priority flow control. This is something that we've discussed briefly the last couple of meetings, I think, looking at adding some level of support for PFC into Corundum. So we got to do some stuff on the hardware side and some stuff on the software side. I'm not sure if we have anybody on the call right now that knows any more about PFC in terms of kind of what's done in current NICs in terms of what do we have to do to map, well, not just current NICs, but NICs and switches, right? How do you map traffic onto priority levels or traffic classes? How do you handle multiple traffic classes efficiently in hardware? And what needs to be done in the driver in terms of configuration and whatnot? I suppose a lot of this stuff we're just going to have to do some background reading on if we don't have any subject matter experts on hand to ask about that. So I think Antonio has been working on this. I don't know if Antonio wants to give a status update, or maybe later. I don't want to put you on the spot necessarily if you're well, Antonio's on the call, but I guess we can discuss this separately if
Sorry, I was unmuted.
Okay.
I was muted. Yeah, I've
you
been
want to
working
discuss a little bit what you've been doing? Okay, yeah, go ahead.
In a Mac control module that will receive a request from the Mac client, which is congested. So this Mac client will send a request asking them this Mac control module to send a post frame to the transmitting side. So that's the idea. Well, I've been looking into the documentation and I have to parse the MAC address. There's a specific value for that MAC address, in which case the MAC, the priority flow control frame is sent. And right now I'm working in the implementation details in the finite state machine and see how to parse the signals. I have two incoming signals, and one for the request of the PFC frame, another one for their data frame. So I've been looking and understanding the documentation. So later in private, I will send you. I will tell you more stuff more clearly because I'm not explaining too much.
Right. Okay.
Well.
Right. So you're basically just working on kind of the first bullet point under hardware, which is the transmitting and receiving of the actual pause frames. Right.
Yeah.
And then you're basically going to implement a module that sits right next to the Mac and handles the pause frames. So I guess you're in the middle of implementation right now. So trying to figure out what things need to do and getting all the pieces put together. All right. Well, that's good to hear. I guess at some point we'll have to test that on hardware once you get stuff working a little bit better. So, all right, yeah, we can certainly discuss more details offline. But it's good to know that that you're doing some work on that and some progress is being made. So, yeah, cool. All right, so that about rounds out what I want to talk about in terms of priority flow control. Now, the piece that I've been working on is the AXI virtual FIFO. I mean, aside from all of the screwing around with GitHub Actions and whatnot. Right. So the idea behind this is to be able to buffer packets in DRAM at, hopefully Ethernet line rate. And what I've been working on is getting the encode decode logic implemented. And this is one of these things where, first pass, you think you know how you're going to put the pieces together, and then you realize that maybe that first idea wasn't so great. So initially I built the kind of FIFO channel module to just have a single AXI stream connection. So you can, just pass data into it, it puts it in the memory, takes it back out, and then gives it to you over AXI stream again. But in order to get these, the data rates and whatnot for the packet sizes that we're interested in and getting everything packed in efficiently, we need to use segments that are, I think, 256 bits wide instead of, the full 1024-bit or the full 512-bit interface to the memory. So we kind of have to cut it in half and shuffle things around on this slightly narrower interface width. So in starting to put together the encode and the decode logic, I'm like, well, I need like per segment FIFOs. But it's silly to FIFO things twice. You got to FIFO it in the kind of DRAM controller interface, and then you got to FIFO it again to get the segments so you can control the segments independently. And I realized, okay, it's probably better if we just split up the FIFOs in the actual kind of channel module. So that's what I'm working on now. I'm getting that updated. So it's not going to be AXI stream anymore, but that's not a big deal because it's only meant to be used, internally connected to the encode and the decode logic. So let's see. I'm working on modifying that, and then once that's updated, then I can get the encode and decode logic all finalized, and then hopefully this will be done. I think there's also a couple of the things I got to sort out in terms of resets, but yeah, that's about it. This is coming together. All right, and that brings me to the last thing that I'm talking about here, and this is also kind of just a bit of a discussion, food for discussion as well. So the idea is to build potentially a switch version of Corundum, and the context here is that there's basically two different research groups that I've been in communication with that are interested in building some sort of FPGA-based packet switch for their research. Well, I mean, they need that kind of functionality. If there was something nice available, I'm sure they would use that instead, but it seems like there isn't really a good comprehensive project. So maybe what we should do is build something custom in Corundum, and then we can iterate off of that. So one question here is there anybody else that's potentially interested in helping implement something like this? I don't know. Open question. We'll see. So that we have people from the main students for both these groups on the call at the moment. We got Antonio and Carlos. They're both PhD students in Spain at two different universities. Antonio is doing some work with PFC, and Carlos needs support for TSN, basically. So, or I guess he's building support for TSN, but needs a switch that's going to be, capable of doing that, of, implementing TSN. So kind of, first pass, what kind of capabilities might this switch need? 10 gig to 100 gig operation with kind of a reasonable port count. I think reasonable is going to be dependent on, what kind of target board we're running on. And also, this is an FPGA, not an ASIC. So, supporting 128 ports of 100 gig is probably not going to cut it. That's probably too much. So, I'm not sure what we're reasonably going to be able to implement, but, obviously, more than 4 ports. If we can get like 8 ports, 100 gigs, something like that, that's probably pretty good. Multiple traffic classes, virtual channels for both PFC and for TSN. You need kind of different traffic classes that are relatively independent of each other. I think PFC is a little bit less strict in terms of exactly how that works. From talking to Carlos, it seems like TSN can have some extremely low latency requirements, which could mean just normal traffic classes are not going to cut it, that something else may be required. But, we'll have to see about that. It is an FPGA, so you want to have like a totally separate switch fabric for low latency stuff as an option that you can turn on, that wouldn't be that big of a deal to do. But you don't want to have a switch traffic or a switch fabric per priority level. That's something that would just be a waste of resources. And then we also need to think about switch capabilities. I mean, it probably makes sense at least to implement Ethernet switching, based on MAC addresses, but potentially more could be done. IP routing or more generalized match action stuff, but there's always a trade-off in terms of, this stuff is going to add complexity, which is going to consume logic resources. So I'm not sure exactly what's going to make the most sense there. But yeah, the key point here is putting together a switch that's going to actually fit on a decent sized FPGA that doesn't use too many resources and can get the job done. Target boards, it definitely makes sense to think about kind of what interfaces might be available on common boards. So for Alveo or similar kind of PCIe form factor boards, they tend to have 2 to 4 QSFPs, which means 2 to 4 ports at 100 gig or 8 to 16 ports at 10 gig or 25 gig. Not particularly interesting at 100 gig, just with 2 ports. I mean, what can you do, right? I guess plus maybe an internal port. At 25 gig, that is a little bit more interesting with 8 to 16 ports. So something like that could be a pretty useful target. But there are other boards available. I know like so High-Tech Global they make 2 things. They make a big honking FPGA board with a bunch of QSFPs on it. They also make an FMC Plus adapter, which has 6 QSFPs on it. So you can get something like a VC118. You can whack one of these 6 QSFP adapters on there. You can get 8 QSFPs on one board. The HTG 9200 gives you 9, and then also has an FMC Plus, so you could add another 6. 15 QSFP28 on one FPGA. That's a lot of bandwidth. I don't know if actually using all of those, connecting all those up to a switch would be reasonable, but you can potentially get that with an off-the-shelf board. So that is kind of that does kind of set the order of magnitude. I don't think beyond 15 or 16 QSFP28, at least with the current generation of FPGAs, is worth thinking about, because I'm not sure there's anything you can get at the moment that has that kind of bandwidth. So does anybody know of any useful references or existing designs that we can look at in terms of putting something like this together? I went ahead and created a channel on the Zulip to talk about the switch design, and I've been hunting down a few resources, a few papers, mainly looking at switch fabrics implemented on FPGAs and whatnot, just to kind of see what kind of stuff is available. But obviously, I think there's still a lot of work to do at this point. This is still pretty early brainstorming here. So
yeah, for the moment,
yeah,
I am also doing some research. I have talked to some people here, and one way they implemented a TSN I think it was in the University of the Denmark, University Technical, I think. DTU. Yeah. They were working with trying to implement a TSN switch. So years ago at least, in which they put like the time shaper module, the traffic shaper module, the task module of the TSN implementation. They were locating it at the input ports. So like in each input to the switch will have one module of that, so you can also prioritize each FIFO if input to the switch individually. But this is like a very TSN case, so maybe we should go for something more general. And also I am doing some other research about the papers you also put in the Tulip channel the other day, more stuff. So there's also too much work to do to at least to have a global idea of which is the proper way to do it.
Yeah, definitely. Well, the other thing that I noticed is that there seems to be a lot of papers on building various on-chip networks, like for network on-chip type applications.
Yeah.
So I'm not sure if some of those techniques are appropriate for, packet switching. Maybe not. I mean, it seems like, kind of a full crossbar is going to be the most efficient way to, well, not necessarily efficient, but the most performant method, as opposed to, building like some sort of a mesh or ring or something internally. So I don't know. I've seen a couple of those papers. I think some of the, just generalized networking stuff that I've seen is talking a lot about, network on chip. So trying to peel that apart from, packet switching for Ethernet networks and whatnot. Not sure. I mean, I'm not an expert on how you actually build switches. So this is going to be a learning opportunity for everybody.
Yeah, sure.
And then there's also the question of, kind of higher level stuff. It's one thing to have a switch fabric that can actually, implement a crossbar or whatever, but then you also have to figure out what you're doing with the individual packets. So, for Ethernet switching, you have to be able to, for each of the input ports, look up the destination for each packet and then, route it appropriately. And then you also have to have like the learning capabilities, I would think. So as packets are arriving, you can see, what source MAC is, and then insert that into tables or whatever. So all of that has to be figured out. And there's definitely a potential concern about, data rates versus packet rates and things like that, we're going to have to take into consideration as well. I'm not sure off the top of my head how some of the commercial packet switches work, right? Because if you have like 64 ports or 128 ports or something like that, you have traffic coming in on all of those ports. You have to make routing decisions for all of that. So do they have like, is it one block on every port? They just replicate, if you have 64 ports, do you replicate that block 64 times? Every port has its own local MAC address table, its own local, IP routing table. I'm not sure. Is there some level of sharing? Is it like every 4 ports or something that are, looking at the same resources? Because some of these tables can be pretty big, I think, at least for IP routing. And you can only put so much SRAM on a chip. You got to have packet buffers and stuff too. So I'm almost thinking, maybe there has to be something hierarchical here. So like, for example, you might have a module that can handle a single 100 gig port and does this kind of routing. Or, if you're doing 25 gig, well, maybe you can have like 4 or maybe 8. Because the packet rate is lower, you have some more cycles perhaps to, do matching, and you can kind of, share resources more effectively, something like that. And then in terms of building the actual switch fabric, I think I found one paper that was talking about doing kind of a hierarchical design where you have several kind of smaller switches that you distribute the data across for different routes you're taking through the switch. So in order to build up the full crossbar. Although one of the papers was like running their switch at like 40 megahertz. I'm like, how does that work? 40 megahertz seems way too slow. But yeah, I don't know.
Yeah, I also saw that, and it was like, yeah, they're really big data width, but only 40 megahertz.
Yeah, it sounded like it had something to do with their iSlip implementation or something. They're like, we're just going to run everything at the same clock frequency. I mean, I guess I can kind of see that argument, but it also makes me wonder about their numbers. Like, okay, so if you were to take a different scheduling algorithm that's, more performant in terms of timing, and you go for narrower data width, what does that do to the size of the switch, right? Could you make something a lot bigger? Not sure. So we might need to start playing around with that.
Yep.
Not sure if anyone else has any anything to add. I don't know, Ulrich, have you guys looked at doing packet switching on your end? Anything like that?
Yeah, we did implement some incomplete switches, let's say. So
Okay.
kind of specialized to support 1 or 2 or 3 interfaces with some a priori knowledge about where packets will go. So what was definitely missing was to put a fully capable route decision logic inside. Yeah, so that it was a simple case, let's say.
Right.
And I guess
Would this-
from a packet data perspective, if it's possible to put a fully meshed XC stream interface in there that's running at a high enough clock rate, then that's fine. But managing all the rules about routing is another point that might get tricky in a generic case.
Right.
And if you require buffers, then yeah, well, usually using the memory interfaces will exhaust whatever you have.
Right. Yeah. 'Cause
Yeah.
that's the other thing is that, there's a limited amount of SRAM on these things. So the more ports you have, you got to start getting more creative with how you're doing the buffering. That's definitely an important consideration.
Yeah, and
Okay.
it depends on how many features you actually like to support, right? So if you're running like pause frame support, then you can't actually rely on bandwidths dependent on the port speeds. It's actually, yeah, it could be any depending on pause frame usage of the remote set. So things get even more complicated. And if you do like replication or whatever additional protocol support, which sometimes are kind of, so that I guess that's one of the problems. People are used to these Arista type big switch implementations, and if you put something into an FPGA, they are usually like, okay, why can't you do this, and why isn't this capable of doing that? That's a standard feature. So that's something why we kind of reverted to doing very specialized implementations specific to like embedded environments where this was good and fine and working. But a more general approach, I guess, the FPGA is the wrong chip. It's just too expensive to implement something that's being done efficiently in a dedicated ASIC.
Right. I mean, I guess the goal here is to support, kind of research related stuff. So
that's for sure. If it's not about selling a product, then you can do everything, and it makes sense to experiment with it. Obviously, yes.
Yeah. So the trick is, I think, coming up with a reasonable level of capability, right? That's going to be enough for the research. But obviously, we're not going to be replicating what an Arista switch can do.
Right.
To feed
so
or whatever.
The feature set must be as small as possible, and then you can experiment with additional features that are not standard on top of it.
Right.
So that's I guess a good approach. Yeah.
Well, I guess part of it is you can make it modular, and then you can substitute in the appropriate implementation of a particular module. So, for example, if we have like kind of an ingress module, which is performing the routing decision or whatever, then you could have a couple different versions of that. The nice thing about being on an FPGA is you can swap stuff like that out without too much difficulty, right? You can't do that on an ASIC.
And the other
too
thing
much
is
difficulty because rebuilding the design might not be easy with timing closure concerns and placement constraints and whatnot. But at least you can reload it versus an ASIC. You got what you got.
Yeah, no way. And the other thing is that I would try to think of in an early step is even if I want to have a specific feature, what about the generality? So is it something that need to be available for all IP ranges or for all MAC ranges, or can I define subset so that the rule space gets so small that I can easily fit it into the device, but without sacrificing the expressibility of the results or attributability of the results for the experiment, right? So, for example, if you want to do some layer 3 matching, then maybe it's enough for your experiment to just use the lowest 4 bits of the IP address, for example. So then the lookup is pretty straightforward. You can directly implement it in LUTs, and you don't have to rely on hashing and whatnot. That might end up of being, yeah, pretty complex, especially if you want to do it in a known latency. So I guess that's another way of reducing complexity, yeah, without sacrificing functionality. But yeah, depends on the experiments, right? So I don't know.
Yeah, that's definitely a good thought as well. It's, I mean, for research stuff, you can do things you wouldn't, normally do in terms of configuration. Yeah, because the routing decision component that can definitely involve, things like cams, which are not so great for implementing on FPGAs. I mean, they can certainly do it, and I know Xilinx has quite a bit of IP for implementing cams and whatnot. I've put together some Verilog for cams based on a couple of Xilinx white papers a while ago, but yeah, that's definitely going to require some thought. Oh, I guess the other thing too, I think Carlos, you were just talking about PTP support as well, because that's something that you guys need for TSN.
Yeah, to keep everything synchronized at least.
Right, yeah. So there's a question of boundary clock versus transparent clock. I think boundary clock is probably going to be easier to implement than transparent clock.
Yeah, more useful
unless
also.
There's unless there's a reason that we need transparent clocks. It seems like most switches, they support either one or the other. So, like I think the big Arista packet switches and whatnot generally only support boundary clocking. But I've got a couple of, what are these? What's the manufacturer of these guys? Ruckus, I think. Kind of lower end switches, but they only support transparent clocking. So it tends to be just kind of one or the other. But yeah, it's like Corundum right now, it basically supports effectively the boundary clock version of PTP, the two-step.
Yeah, I think it is
so,
implemented in the PTP for Linux
probably,
also.
Right, yeah. I mean, I guess PTP4L could probably use either. It's just a question of whether the hardware supports it. But it's like to do the one step that you need for transparent clocking, the Mac modules on transmit have to be able to modify the packet as it is being sent. And that, let's just say that adds a lot of complexity. The other thing that I need to figure out too is how to potentially reduce the resource consumption of some of the PTP kind of supporting logic and whatnot. It's one thing attaching, 96-bit timestamps to packets. At 100 gig, I think that's less of an issue versus at some of the lower rates, where attaching a 96-bit timestamp can be, if you don't do that in a smart way, then it eats up a lot of block RAMs and whatnot on the FPGA. But the other one is all of the PTP CDC logic to transfer the PTP clock into all the Mac clock domains. With Corundum, if we only have, 2 Macs or whatever, it's not really a big deal if that module takes up a bit of space. But if we're putting 16 or 32 Macs on there, I did some work, right? I talked about last time to reduce the size of the Mac by improving some of the CRC computation. Which, that's all well and good, but the PTP CDC logic is a lot bigger than that. So I think
maybe in the future.
I thought about that recently. Like, do we actually need to transfer the whole timestamp, or can you just transfer, say, like the lower, 40 bits or something like that? Just a couple bits of the seconds portion. And then all the nanoseconds portion, and then reconstruct it, because realistically, how long are these packets going to be hanging out inside the data path? You might be able to just kind of fetch the upper portion of it and use it, as opposed to having to schlep that around. So not sure. I'll have to take a look at that at some point.
Yeah, I think if this is a problem, we should try to address it.
Lots of stuff that we can potentially, optimize and adjust moving forward. But yeah, we got some work to do. I think that's the conclusion here. Some work to do, some reading to do. Yeah.
Yeah, good.
It's relatively common that we'll have Bob from Cisco on the call, and they know a lot about packet switches, but he didn't join today, so I guess maybe we'll have to follow up with him separately. I mean, I think Bob is more on the NIC side of things, but he probably has a lot of people that know more about the switching side of things that we could bounce questions off of. So potentially, always got to utilize all the available resources, right? All right. Well, that's it in terms of my slide deck here. So we can now open it up to, questions, comments, whatever. So I'm not sure. Does anybody have any questions or comments about anything? We'll let everybody other than MLE go first before MLE runs away with it. So I don't know, Antonio, Carlos, any points you guys want to make?
Well, I am currently implementing some tests in CocoaTV for my TSM modules.
Okay.
I don't know if this is this meeting, I don't think it's for that, but maybe I can ask you something now. It's fine.
Sure, why not?
Okay, I work with the access string interfaces. So if I want to add like an additional signals, but that aren't part of the axis bus, of the axis stream bus, and use it like at the same time like inputs to the system. How can I manage to take them into account, that to also like follow the same, to keep them constant, for example, until the frame reaches the sync. You know what I mean?
Right. So the idea is that you're going to have some separate signal that's not part of the AXI stream interface. So you don't want to put it on T user or something like that.
No.
But you want to change that in concert with the data being moved over the AXI stream. So I don't think the model supports doing something like that, but you can always sort of write your own HDL kind of in CocoaTB, right? You can look at the AXI stream signals and generate or delay or whatever this separate signal based off of those. That's probably the most straightforward thing to do. I'm not sure if that kind of approach would work for the signal that you have in mind. Like what are you trying to do exactly? So you have,
for example,
you have transferred via AXI stream.
And imagine you have the axis bus and you have to do something on the input frame from this axis bus based on of an input signal. That's indicates you, for example, if you have to change something in the frame, to change, for example, the header. And only if this signal is activated, you have to perform some processing. If not, you just pass through the frame.
Okay. Oh, and you want to have you want to send several frames into your code and have it process, some of them.
Yeah, you are once you will do something, others not. So yeah.
And you're not using any of the sideband signals right now, right? It's basically just
the what?
Data. Are you using any of the sideband signals like TID, TDEST, T-user?
No. I only the only signal is
the
T-user. T-user is the only one that I am also passing through.
Right. Okay. Yeah, I'm not sure off the top of my head the best way to do something like that, because it would be pretty straightforward if you were to connect that to T-user or something, and then you can set a bit in T-user, and then it'll drive the signal into the design.
Well, one possibility is to redo the EHDL for the sake of the experiment, only for the test, like tune it a little bit.
Well, okay, so one thing that you can do with CocoaTB is the test code that you have doesn't necessarily have to be the top level code, right? So in most of the tests that I have, I just like doing that because it's simple, it gets the job done, you don't have any futzing around with anything, but you can create an additional Verilog module that instantiates your test code and potentially has a little bit of additional HDL in it. So you can potentially kind of place your signal onto T-user or something, and then connect that to the test bench. So you wouldn't have to modify your HDL, but you could kind of present a slightly different interface.
I see.
Cocoa
Maybe
TV.
that will work.
That
I
would
think.
probably be the way to go in this particular case.
Yep.
I've been talking to the Cocoa TV guys about having some kind of HDL-like transformations that you can perform in, from the Python side of things. Like, could you take two signals and concatenate them together and then pass that off to a BFM to drive or to read from or whatever? Or something that I use occasionally is, where I have multiple interfaces kind of concatenated together. Well, can we take a piece and hand that off? Because you can do that very easily in Verilog. But Cocoa TV doesn't have abstractions to support that sort of thing. So eventually, maybe we can do it straight from Cocoa TV. But for the time being, we may need to do a little bit. We may need to help it a little bit with some HDL. So I think there's actually some of the Cocoa TV guys that prefer doing a kind of Verilog top level. They'll do like the clock generation in HDL instead of in Cocoa TV, and maybe a couple of other things. And then you can connect the Cocoa TV models. They also don't have to connect to the top level. You can connect as far down the hierarchy as you want. So
good.
That's definitely something to consider doing.
Yep.
And there's a few cases in Corundum that, due to limitations in Cocoa TV, I have HDL set up such that I can connect a Cocoa TV, model down a couple of hierarchy levels and have it work properly.
Okay, thank you for your answer.
Yeah, that's fine. All right. Well, I guess if nobody else has any questions or comments, then I'll turn it over to MLE. Ulrich, do you guys have any questions or comments, or not today? I don't know.
No, for today, I think I don't have anything.
Okay.
Not sure if
I guess I don't see Joachim on today, so I guess is it a holiday for you guys, or is Joachim busy?
No, I guess he's busy around.
Okay, well, it happens.
Yeah. So no, I guess now nothing on our side. Yeah, next week I hope I can prepare something and see and I can report if the firmware update procedure actually does work somehow.
Oh, right, because you guys are working on talking to the SDM on the Intel devices, right? So you need to,
I implemented most of the commands that are available now, and I just started to, or maybe I actually coded most of it together to do image updates.
Okay.
Yeah, I just finalized it yet and didn't test it yet. So the interesting part will be kicked off during the next days.
Will it work?
Yeah.
Or will you brick the board?
so somebody needs to be where the board is, so that if I brick it, he can hook up a JTAG cable.
Oh, you don't have a JTAG cable hooked up already?
Yes, we do have, but there is a Linux PC attached to it, and then you can't, with third-party programmers, you can't flash with a Linux system. So you need a Windows system, and we are a little bit limited on having those available in the lab right now. And
wait, you can't flash it from Linux? Or
not with the cheap programmers.
Oh, I see. You don't have the Intel USB blaster things. I see.
Yeah, we do have 2 of them, but usually we don't hook them up in the setups that are running for a long time, because then we would block them and nobody can use them. So
right.
We usually
and
use
those are slightly expensive. So yeah.
Yeah, they're like, and they haven't been available for a long time. So we were waiting for them
really?
like months, and then they were available again, and then we bought pain. 2 of them. Yep. Now we have 2, so that's fine. But we have like 10 of the cheap ones. Yeah.
But the software support for those is spotty, or you need to what I think they like give you a DLL or something. You gotta drop that in the Cordis directory or
Yeah, that's exactly
like
the
that.
way it is right now. It's like it has been on the Xilinx side until 5 or 10 years ago when Xilinx started to ship the drivers for the digital adapters. Back then, so before that, before Xilinx took over about the distribution channel, you had to do the same on the Xilinx side. So there were some special DLLs from Digiland. They even had their own flashing tools. I never used them, but we used the special DLL
right.
that you
yeah,
knew.
I remember
Yeah,
that.
yeah, yeah.
They had their
And
own.
Yeah, back then.
But at least Digiland eventually made Linux versions of those.
Yeah. So the program is working fine, other than flashing. So that's the only thing that somehow doesn't work on Linux. I don't know why.
Well, okay, interesting.
It's most probably that something is different. Maybe actually, maybe I have to retest. So it might work for reflashing, but it definitely didn't work for the first time flash of the device. Because then you need to set some special registers, like the non-volatile configuration register inside the flash. And I think that didn't work out. I don't know what happened there. What's the specialty of this command? But yeah, so there's something in the driver that happened, and yeah. So maybe as all the cards are in use and already contain a valid image and that I booted them, so maybe I can override using the way we hooked it up right now. Good trial. So I think I will brick one device anyway. I will check that.
One thing that you can try doing is instead of just going for broke and dumping the whole, rewriting the whole flash, just try just as some test reads and writes, like just take the highest page in flash or something like that. And
yeah, that worked fine.
Poking at that. Oh, that worked fine.
Yeah.
I see.
Yeah. So I am able to read and write from memory, and I tested this. But you again have to, I don't know, swap bits, and yeah. So there are things that might get wrong during upgrade procedure, and I guess usually, yeah, if it hasn't been tested, it will go wrong. So
right.
Most probably it will go wrong.
So the code that you've put together for doing the update process, are you taking in just a binary file, or are you reading a POF, or what?
Yeah, so I'm reading in two files actually. One is the map file that's generated by the programming file conversion tool. I don't recall the exact name, and there are two tools that do similar things but not the same. They basically you configure which bit streams are going to be used, like the soft files, and you can use multiple ones to kind of do fallback measures during boot, and that's the ultimate target here. Then one binary file is provided. It's an RPD file, I guess, which contains multiple binaries. The first one is the STM firmware, then a factory image, multiple, let's say, headers, so description of partition blocks, and then multiple partitions that may contain various bit streams. And
so does
what
that
is
file
part of this
correspond
file,
like one-to-one with the flash, or is it kind of a higher level format that you have to interpret?
No, that's basically, other than the bits juggling, it's one-to-one corresponding to the flash.
Okay.
But there is an additional file provided, the map file, which then is a text file and contains which is actually, so what partitions are actually located where inside this binary file. And that's important in the case where you want to just update
where you don't want to do the
one
whole
of
thing,
the
but just
images.
some parts of it. Yeah. Okay.
Yeah. And yeah. So I guess I'll do like a two-step test process. The first thing is I need to swap out all the configuration, including everything, because the default mode is if you don't add something like factory images and so on, you just get an image with the STM firmware and the single bit stream that you want to be loaded. And yeah, to go away from this procedure, you have to refresh everything. I don't know why. I would have expected that generally the descriptions and everything is already there, so the blocks and so on, but just there is one factory image and that's loaded all the time. But no, so nothing is there. It's just the STM firmware and the single bit stream. So we have to swap this out into something that actually has a factory image in. And then in future steps, we could just swap out the application image. And the good thing is, if this is in place, then if something goes wrong during this update process, it would so the card is being repowered and it would revert and fall back to the factory image, and you can set the process up again and update the application image. But you're still having a workable card, so it's running and it's accessible, and you can talk to the STM again. So that's the idea. So its first step is update everything. Second step is providing measures to just updating the relevant parts, but not sure yet which parts are the relevant parts.
Right. And then I think there was also something, at least this was alluded to in some of the bitware documentation, that there's a dependency between the SDM firmware version and the Quartus firmware version.
Yeah, so what I
apparently
read out
trouble.
of the that might actually happen. So I just found out so far one thing, and that's depending on the Quartus version, the firmware will change. Because newer Quartus versions may provide fixes, additional features, whatever, into this firmware, and so that it's a different firmware than the older, than the one delivered with the older Quartus version. I don't know if you could generate a bit stream which actually depends on a newer firmware. I don't know about this one. It might happen because in some process during booting, there is calibration taking place on the P tiles or the H tiles on L tiles and whatever. And I'm not sure if this is actually controlled by the STM or not. But definitely what happens is if we boot the card and the bit stream requires a PCI Express interface, it won't load until there is a clock detected on the PCI Express interface. So the configuration actually gets stuck because there is some calibration scheduled into the boot process of the FPGA, right. So there's and this check is right in front
to some
of.
extent, that's not particularly surprising because I know Intel does the configuration over PCI Express. And that's
right.
Apparently pretty common to do. So yeah, and it'll basically be, we're going to bring up the PCI Express link and then we're going to do other stuff. So that one in particular, at least, is not too surprising. But it is annoying. It's like, why is this thing not working? Oh, we forgot to connect the clock to PCI Express on the board or whatever, and it's waiting for that.
Yeah, and in this case, as there is such things in place, I'm not sure if there is other things in place that kind of may create an FPGA image require an updated firmware in the STM. because that's really annoying. And especially if you don't know about, because then you have to always update also the STM procedure, or at least when
you
you
don't
change the
necessarily
Quartus
always
version.
have to do it, but you can read the current flash for the SDM firmware and see if it matches what's in your update package. And if it does match, then you're good. If it doesn't match, then you gotta be, uh-oh, we need to reset something here.
Right. And then if something happens during the update, then okay. Hey customer, please send back your brick card. Not nice.
Yeah,
I
mean,
not sure.
The only reason
actually.
I mention that is because I know that some of the documentation for a couple of the bitware cards has some disclaimers about that, saying that you got to use a particular Quartus version. If you need to use a different Quartus version, then you may need to go through this process where you got to like install a jumper and yada yada yada. I'm looking at this going, what?
Okay.
What is going on here? So I don't know exactly what the problem is there, or if this is just like a, you know, trying to keep all their bases covered sort of thing.
Yeah, maybe, but because maybe they also just don't know what Intel does, and so they are just trying to stay on the safe side.
Intel told
and
them
they
that there
usually
is some dependency there. Yeah,
exactly. And usually what definitely is the case is the bitware guys usually have some onboard controller that actually configures the FPGA. So what might be the case is that their flash layout is different and they have to do, I don't know, translation or whatnot to actually support this. And they might select different STM firmware images based on conditions. so usually you cannot just update the flash using the standard vendor way on bitware boards. You usually use a bitware tool
for
it.
whatever reason, this doesn't seem to be a bitware specific thing. This seems to be kind of an Intel thing, where they, for whatever reason, because Intel dev boards are built like this too, where they have some stupid FPGA that sits in between the big one,
the Max 10 guys. Yeah,
I don't know why they do that. It is highly annoying because it means that, you know, the big FPGA can't talk to the flash directly without going through the firmware on the little FPGA. And, you know, unless somebody sits down and adds provisions to support that, it's impossible to update the flash over PCI Express. So like I have a Stratix 10 DX dev board. It's impossible to implement flash update over PCI Express because there's no provisions and no connections for that. You know, even if you were to modify the firmware yourself on the Max 10, they don't have any wires that you could use to talk to it. It's like, what the heck? The FPGA can talk to the QSPI flash directly. Just delete the Max 10 and we're good. I don't understand it.
Yeah, I never got it as well. I just remember that once we used the bitware board, there was always this. The board was always hooked up to some PC using USB cable or something and some proprietary software to do something with the flash. Yeah.
Oh, I did manage to at least partially reverse engineer the bitware's USB protocol for talking to these guys. So you might be able to do something similar, because I had to flip the flash partition that it was using. And they have some screwy way of doing that using their controller. So I was unable to boot the thing from flash until I figured out. And the hard part is I didn't have their programs. So I had to reverse engineer the protocol without a working thing to probe. Fortunately, it was documented sufficiently somewhere that I was able to kind of piece it together and make it work. But yeah. Speaking of which, I need to clean that utility up and stick it in the Corundum repo, just in case anybody's using this board and they want to boot it from flash. The other annoying thing is that the flash selection is the partition selection is persistent, and if it fails to boot off the main partition, then it switches to the secondary partition permanently until you go poke it over USB and switch it back. It's like, come on, guys, really? I'm not sure why they do it that way. I'm guessing it's so they have the ability to force it to boot from the fallback flash, despite Xilinx's fallback method basically. So like the FPGA can do it automatically, but if you want to control which partition it's running under, and also the split in the flash is not equal. They have like one small partition and one large one. It's a little bit screwy how it's set up, but yeah, that one had me going for a while because I flashed the thing from Vivado. It's like everything looks good, but it doesn't boot. I'm like, what? What's going on here? Anyway, one thing that I was going to mention as well is that I spent some time a while ago putting together a couple of little Python programs to parse the POF and SOF file formats from Intel and just extract the data. I don't know how that compares to the map file plus whatever binary that you get out of the programming tools, because I think you can probably generate a POF as well. That's just everything in one file. I can send you those Python scripts if you want to take a look, or I'll post them on Slack or whatever. I don't know if the SOF one is useful because I don't know how you get from like the SOF data to what's in the POF. They look completely different. It's not like bit swapped or something like that. So I don't know what kind of transformation the programming tool is doing. Because to some extent it would be useful to have the SOF file, like in the firmware update package, because then you could just push it to the board via JTAG directly as opposed to right into the flash. You can do that with the bit files for Xilinx, right? I mean, the transformations you do to those run right them out to the flash are pretty straightforward. But I don't know what's going on with the Intel devices. But yeah, I guess the other thing that we should think about too is if we're going to make some sort of a firmware update package for Corundum that will work on both Intel and Xilinx devices, we should start getting the details on that fleshed out. So I think we discussed this a little bit before. If we do like some sort of a zip file, we can put binaries in there. We can put like a manifest file. We can, I don't know if it would make sense to put that map file in there. Everything inside of one file that the firmware update tool can look at and interpret and then write the right things to the right partitions. So it's like if we have like a manifest file in there that can say, okay, here's the partition for the primary flash, here's the partition for the fallback flash, here's the procedure for doing the update, what needs to be checked or whatever, if that makes sense.
Yeah, I was aiming at playing around with it, getting it into a state where it kind of works for us, and then try to extract like the more general aspects, because just working off from documentation is complicated in this case, I would say, because it's very different for different FPGAs actually. So it seems as if the Stratix 10 series is quite different than the ones before. So even like they don't recommend to use the same tools, or even that those tools doesn't work. So that was the reason why I was getting to implement something workable first, and then see how to actually come up with a more general view on it, and then migrate to that.
Right. Okay. Yeah, that sounds reasonable. Let's see. I'm going to go ahead and put these Python scripts on the Zulip right now. Well, let's see. Is there anything else that we need to discuss, or have we pretty much covered all the main topics that people want to discuss?
Nothing left from my side.
All right. Got the firmware updates. We got the PFC. We got switch. All right. I think that's all the main stuff from my side as well. So I guess we'll go ahead and call it a day for today, and see everybody in 2 weeks, and maybe we can meet with the Antonio and Carlos before then to try and coordinate on the Switch stuff, or anybody else that might be interested in Switch and working on the Switch. Yeah, we have the channel on Zulip for that, so if that interests you, then connect up with that, and we can take it from there. All right. Let's see.
Okay,
I guess
great.
so. Today is the 30th. 2 weeks from now is going to be what? February 13th, I think. So sounds good. All right. See you guys in 2 weeks. Thanks for tuning in.
See you guys.
Okay, good. Thank
See
you.
you. Thank you.
Bye bye.
Bye.